How do you possibly manage the temperature, pressure, and flow in thousands of different pipes, all at the same time 24/7? Well, it might seem impossible, but it's happening right now, and it's all thanks to the principles we're about to break down.
So, here's how we're going to tackle this. First, we'll look at the basic challenge of automation itself. Then, we'll dive into the senses of a plant, how it measures things like pressure, flow, level, and temperature. After that, we get to the cool part, the brain, a system called PID. And finally, we'll put all the pieces together to see how a complete control loop actually works.
At the heart of all of this is one incredibly powerful idea, the feedback loop. It's really just a simple, constant cycle. You measure something, you compare it to where you want it to be, and then you act to fix the difference. Think of it like a three-step dance that just repeats over and over again. Measure, compare, act. We're going to see this pattern again and again.
Okay, first things first, let's talk about how a plant actually feels what's going on inside. We're going to start with two of the absolute fundamentals in any industrial process, pressure and flow.
So to measure pressure, engineers often rely on two classic mechanical tricks. On one hand, you've got the Bourdon tube. This thing is the tough, reliable workhorse. You can think of it like one of those party horns that tries to uncurl when you blow into it. Then you have the bellows, which is much more like an accordion. It's way more sensitive and can expand and contract a lot more, making it perfect for finer, more delicate measurements.
The genius of the Bourdon tube is just how simple it is. It all comes down to its shape. See, it's not a round tube. It has an oval cross-section. When you pump pressure inside, the tube naturally wants to become more circular. And as it does that, the whole C-shape straightens out just a tiny, tiny bit. That little movement is all you need to move the needle on a pressure gauge. It's just brilliant engineering.
All right, now what about flow? Well, fun fact, we usually don't measure flow directly. Instead, we measure it indirectly. We stick an obstacle in the pipe and then measure the pressure drop across that obstacle. The cheapest, simplest way to do this with an orifice plate. It's literally just a washer, a metal plate with a hole in it. The much more elegant but expensive solution is a Venturi tube, which is carefully shaped to guide the fluid smoothly.
So here's the key bit of physics that makes an orifice plate work. It's this idea of the vena contracta. As the fluid squeezes through that hole, it doesn't immediately spread back out. It actually continues to narrow for a short distance after it passes the plate. Right at that pinch point, the fluid is moving its fastest, which means its pressure is at its absolute lowest. So by measuring the pressure before the plate and right at that pinch point, you can figure out the flow rate. Pretty clever.
And this table right here perfectly sums up a classic engineering trade-off. The orifice plate, it's cheap and super easy to slap between two pipe flanges, but that sharp edge creates a ton of turbulence. You lose a lot of pressure permanently, which means you have to spend more money on a bigger pump to make up for it. The Venturi, on the other hand, is pricey and bulky, but it's incredibly efficient and can even handle liquids with solids in them without clogging.
All right, let's move on to our next set of senses. We've got pressure and flow down. Now we need to know two more critical things. How much liquid is in a tank, and of course, how hot is everything? So let's talk level and temperature.
For measuring the level in a tank, the most common tool by far is a differential pressure cell, or a DP cell. It's pretty straightforward. It just measures the pressure at the bottom of the tank. The more liquid you have, the more it weighs, and the higher the pressure. Simple. But what if that liquid is something you really don't want to touch, something super corrosive or even radioactive? That's when you use a bubbler system. It cleverly pushes a tiny stream of gas down a tube and measures the back pressure it takes to make bubbles. The instrument itself never even touches the dangerous liquid.
Now, this is a super important real-world detail about using those DP cells. Imagine you have a boiler running at, say, 5,000 kilopascals, but the actual change in pressure from the water level might only be 30 kilopascals. If you accidentally hit one side of that sensitive DP cell with the full system pressure, you'd destroy it instantly. So to prevent that disaster, technicians use what's called a 3-valve manifold to very carefully and slowly equalize the pressure on both sides before they take a reading.
Okay, temperature. Here we've got two main players. First is the RTD, the resistance temperature detector. This is your high-precision instrument. It works because the electrical resistance of a pure metal, like platinum, changes in a very predictable, very linear way as it gets hotter or colder. Then you've got the thermocouple. This is the rugged, cheap, and simple option. It's based on this amazing physical phenomenon where if you join two different types of metal together and heat them up, they actually generate a tiny electrical voltage. So it all comes down to picking the right tool for the job, right? If you need pinpoint accuracy for a chemical reactor, you're going to pay the extra money for an RTD. It's also less affected by things like radiation. But if you just need to measure a really high temperature on a vibrating piece of equipment and cost is a factor, you grab a cheap, durable thermocouple. It's all about the specific application.
All right, we have covered the measure part of our loop. We've got the senses. Now we need the parts that compare and act. We need the brain of the operation. So let's talk about the algorithm that runs pretty much every industrial process on the planet, PID control.
The P in PID is for proportional. This is the most intuitive part of the whole system. It looks at the error right now, in the present, and it takes an action that's proportional to how big that error is. So if your room is 2 degrees too cold, it turns the heater on a little bit. If you're 20 degrees too cold, it cranks the heater all the way up. Simple as that.
Next up is I for integral, and this part is all about the past. See, proportional control on its own has a little flaw. It often leaves a small permanent error. It gets you close, but not perfect. We call that an offset. Integral action fixes this by looking at the accumulated error over time. It's like the system has a memory, and it says, hey, we've been 2 degrees too cold for the last 5 minutes. Let's give it an extra little push to get all the way back to our target.
And finally, D is for derivative, and this part tries to predict the future. It doesn't care how big the error is, it only cares about how fast the error is changing. So if it sees the temperature flying towards your target really, really fast, it steps in and says, whoa, 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 slow down a bit. Let's ease off the gas now so we don't blow right past our target. It's basically the brakes for the system.
So how do you combine these? Well, P only is pretty rare because of that offset problem we talked about. You'll almost never get perfectly on target. That's why P plus I is the absolute workhorse of the industry. It's used in over 90% of control loops because it gives you stability and precision. You only add the D for really slow, sluggish systems, like trying to heat a giant tank of oil. You need that predictive braking action to speed up the response without overshooting.
This quote right here nails the most important takeaway. Proportional control will get you in the ballpark and make things stable, but it won't get you a bullseye. To wipe out that last little bit of error, to get things perfect, you absolutely have to have integral action. Okay, we've got the senses and we've got the brain. So for our last section, let's put all of these pieces together and see what a complete working system actually looks like.
So let's imagine a simple heat exchanger. First, an RTD, our sense, measures the temperature of the liquid coming out. It sends that signal to our PID controller, the brain. The brain then compares that temperature to the set point, the temperature we want. If it's too hot, the controller calculates the right response and takes action. It sends a signal to a control valve telling it to open up a bit and let more cooling water in. Measure, compare, act. There's our loop.
And this chart really shows you what happens when the system gets knocked off balance. With proportional only, you get a fast reaction, but you see, it never quite gets back to the target. It settles with that offset. Now add integral action. The response is a little slower, a bit more methodical, but look, it brings the error all the way back to zero. Perfect. And when you add derivative, you get the best of both worlds, a fast, aggressive response that settles right on target without a lot of messing around.
And that brings us to a final question to think about. For the better part of a century, PID has been the undisputed king, the brain of industrial control. But now, with AI and machine learning getting so powerful, is that about to change? Or is the real bottleneck for automation not the brain, but the senses, those tough physical instruments that have to survive in the real world? Something to think about. Thanks for tuning in.